Well, we're in for a problem tonight. I needed to make this video for you, but I realized I left my iPad at home. So today I am balancing my camera on my cooking spray can and doing this paper and pencil. Real old school. But it's super important because I wanted to help you understand better the Squeeze Theorem, or also known as the Sandwich Theorem or the Pincher Theorem. And remember last time in class we talked about that if we have a function g of x and we know that it's between h of x and f of x, when x is near a variable a, then if we also know that the limit as I approach a constant a for f of x, if that limit is equal to the limit as I approach a of h of x, then we can say that the limit of g of x as x approaches a equals L. So I'd like you to take out the worksheet that we did in class and we started taking notes, and it was on the Squeeze Theorem. And I wanted to talk through a few more additional examples to help make this clear. Now I find that I typically use the Squeeze Theorem when I have a trigonometric function, because when looking at this trig function, I can squeeze in sine of x between two functions, right? So if you think of your sine graph, we have the basic sine graph going like this, right? And we know that sine is squeezed between positive 1 and negative 1, right? So we could say that negative 1 is less than or equal to sine of x, which is less than or equal to 1. Now I'm really concerned about those sine of x divided by x, not just sine of x. So what we can do then to be able to obtain the function sine of x over x is I can divide every single portion by x. And I can allow to do that by the property of equality. So now I have the function negative 1 over x is less than or equal to sine of x over x, which is less than or equal to 1 of x. So the question is, do I know the limits of my outer pieces? So do I know the limit as I approach infinity of negative 1 over x? Do I know the limit as I approach infinity of 1 over x? And yes, I do, because this is a function that is common to me. We know that 1 of x looks like this. So therefore, negative 1 of x would just be the opposites of that. So we can see as we approach infinity, this limit is 0. And this limit would also be 0. So therefore, if I take the limit of the left piece as I approach infinity, and the limit of the right piece as I approach infinity, and we know that it's 0, and the outer piece is also, therefore the limit of the inner function as I approach infinity will also be 0. And that is using the Squeeze Theorem. So now what I'd like you to do is try an example on your own. So your example is, what is the limit as x approaches 0 of x times sine of x? So you'll pause the video, well, the video will pause for you, and then you will make your choice. Okay, the solution to this. Let's see how you did. Now again, I look at my expression and I ask myself, is there a part of this expression where I know that it is sandwiched between two other functions? And yes, I know that sine of x is sandwiched between 1 and negative 1. Now I'm not interested in just sine of x, I want x times sine of x. So I'm going to multiply every piece of my inequality by x, which I'm allowed to do by the multiplication property of equality. Now, this will only work if I know the limit as I approach 0 of negative x and the limit as I approach 0 of x. Well, these are both two common functions for me. They're linear, and we know that negative x would be 0 at 0 and x would be 0 at 0. So therefore, if I take the limit of the piece that is to the left of x approaches 0, lesser than my function of interest, and if I take the limit as x approaches 0 of the function that is greater than my function of interest, and these are both 0, so then I can therefore by the sandwich theorem declare that the limit as x approaches 0 of x sine of x is also 0. So this would equal 0. I hope you did well on that. Now, let us move to another topic associated with the same idea. That's my buzzer for my dinner. I made rigatoni. I hope you had a healthy dinner. So, the next section is using known limits. Well, we have just finished dinner. My tummy's full, but it's time to get back to calculus. So, prior to dinner, we talked about the Squeeze Theorem, or the Sandwich Theorem, or you may call it the Pincher Theorem. But now what we're going to do is we are going to look more at some limits with trig functions, but what we will do in order to evaluate them is use known limits to find other limits. Oh, let me slide my fancy page. There. Okay. Now there are two limits that we have investigated pretty thoroughly using our graphing calculator. One of them is this first limit. Now this is the limit as x approaches 0 of sine of x over x is equal to 1. So we have looked at this limit and know that this is to be true. So I'm going to use this as a building block to find other limits. Now another limit that is very important is just basically it's reciprocal. Ooh, easy for me to say. And that is the limit as x approaches 0 of x over sine of x is also equal to 1. So using those two givens, let's see if we can use that to find the limit as x approaches 0 of sine of 5x over x. But actually, we're not going to do this. You're going to do that because you have an example on your worksheet from notes that was similar to this. Now see if you can apply that. So find your answer, make a choice, and then come back for the result. So how'd you do? I hope you nailed it. So here we go. This is how it works. So I look at the expression. I notice it's 5 of x over x. But in order to use this limit, I need the sign quantity to be the same as the denominator. So in other words, I need this denominator to be 5x. So what I'm going to do is I'm going to multiply both the numerator and the denominator by 5. So basically I'm multiplying by 1. And when I do that, I have the limit as x approaches 0. Now you always have to write that limit as x approaches 0 each time because it doesn't go anywhere until I actually take the limit of 5 of sine of 5x all over 5x. Beautiful. This is the piece I want. So what I'm going to do is I'm going to use my properties of limits. So the limit as x approaches 0 of 5, which is a horizontal line, times the limit as x approaches 0 of sine of 5x over 5x. So the horizontal line 5 always will have a limit of 5, no matter what constant you're approaching. And then sine of 5x over 5x has the limit of 1 as x approaches 0. So the solution is 5. How did you do? Did you get that right? I hope you did. Okay, now let's move along. Fancy paper switch here. Dun, 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 dun. Beautiful. Okay, now this is another limit that is going to be a limit that we will know very well. But before we know it, we got to prove it. So let's do some math here. Well, algebraically, the first thing I would do is try to substitute. What's cosine of 0? Bing, 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 bing. Cosine 0 is 1? Right. So we get 1 minus 1 is 0 over 0. 0 over 0 is the undeterminate form, which tells me that I have to keep going. Don't give up. Persevere. Show grit and tenacity. Okay, so next then, after I substitute, now I'm going to try to rationalize. Oh, that means multiply by the conjugate. Well, what is the conjugate of cosine x minus 1? Well, of course, it is cosine x plus 1. Now, I'm not sure if this is going to get me anywhere, but you know what? I'm going to try. And if it doesn't work, I'll try something else. So now I have the limit as x approaches 0, and I multiply the two binomials. It's a difference of two squares. So I get cosine squared x minus 1 in the numerator. Oh boy, that makes me excited because I kind of know what that means. X times cosine x plus 1. Do you know cosine squared x minus 1? What's another way of expressing that? Do you remember your Pythagorean theorem for trig functions? Sine squared x plus cosine squared x is 1. So therefore, the numerator has a value of sine squared x. Now, why does that make me happy? Because it just breaks up the expression a little bit, and it might give me a pathway to a solution. Ooh, do you see sine of x over x embedded there? I do, and I know that value is 1 as x approaches 0. So can I rewrite this expression so I have sine of x over x? Well, we know sine squared x is sine of x. Another way of writing that is sine of x times a quantity sine of x. So then what we can do is we can rewrite this fraction as sine of x over x times sine of x over cosine x plus 1. So just a little bit of fraction work. So the limit as x approaches 0 of sine of x over x, whoo, that is 1. Okay, I'm writing it out as you can see. Sine of x over x times the limit as x approaches 0 of sine of x over cosine x plus 1. Okay, so sine of x over x is 1. Now what's this limit? Let's substitute and find out what's sine of 0. It is 0. And then 0 over cosine of 0 is 0, so I get 0 over 1, which 0 divided by 1 is 0. So the solution is 0. So that means that this limit here has a value of 0. Very important. Highlight that fact. It's a good one. Okay. Well, I ran out of memory, so I'm making part 3 of this video. So we have 3 known facts. Sine of x over x equals 1 as the limit approaches 0. Limit as approaches 0 of the reciprocal is also 1. And the limit as x approaches 0, cosine x minus 1 over x is 0. So now using those known facts, let's see if we can now find the limit of an unknown fact. So when I take a look at this, I ask myself, is there something here that I can see that is on one of my known facts? I notice the numerator looks like this limit, and over sine x looks like this limit. So let's break it apart and do some work. Break it down. Bump, 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 bump. That's right. That's how we roll. Okay, so we have cosine of x minus 1 in the numerator. We'll say that's over 1 times 1 over sine of x. Now, I want this to be cosine of x minus 1 over x. So if I multiply by 1, but I'm really multiplying by x over x, I'm going to get in the denominator what I want. Now here, I need this to be x over sine of x. So again, I'm going to multiply by 1, or x over x. So now what I have, now remember, keep writing that limit as x approaches 0. Now I notice when I hold the camera like this, my hand keeps blocking the view. So now I've got x, and then it's cosine of x minus 1 over x, which is the limit of interest. And then here, now I've got x over sine of x, but then it's times this 1 over x, right? And so this is the limit of interest. So when I just using multiplication facts, I know the order doesn't matter. So I have x over x times cosine of x minus 1 over x times x over sine of x. Oh, isn't this beautiful? And it's all as the limit of x approaches 0. Well, we know that x over x is just 1, okay? And then, so that's 1 times, and cosine x minus 1 over x as x approaches 0 is 0, and x over sine of x is 1. So 1 times 0 times 1 is 0. So the limit of the original function here is 0. And we used known limits to come up with that. Now you're going to try one more on your own. Here we go. The limit as x approaches 0, and I'll move my hand out of the way, right, of tan of x over x. So go ahead and try that. Okay, so now you did this problem. Let's see how you did. Now I notice it's tangent x over x. Well, that's not one of my known limits, but I know sine of x over x is. So can I rewrite tangent? Well, we know tangent is sine of x over cosine of x. And then we have this times 1 over x. Ooh, I can see a sine of x over x. Can you see it? So if I rearrange this using the properties of multiplication, so I'd get sine of x over x times 1 over cosine of x. And now let's attempt to find the limit as x approaches 0. Well, we know the limit of the first term as x approaches 0, that is 1. And then if we substitute 0 into this, what is cosine of 0? We know it's 1. So 1 over 1 is 1. So the limit of this expression was 1. How did you do? Did you get it right? I hope so. We're going to try more of this in class tomorrow.